I'm David Stamps. I'm a volunteer at the Belknap Mill, and today I'm going to talk to you about the power, how the power comes in and is used at the Belknap Mill. Okay, we're looking at the Winnipesaukee River, right at the Avery Dam area. This is part of the water that comes out of the watershed. And it goes into, on the far side, there's a powerhouse, which is now hydroelectric power. But if you look at this here, these gates used to control the water flow in and out of the two, the Buzzell and the Belknap Mill. And the water would literally flow into the mill itself. You can see where that archway is, and then we'll talk about what happens once it got inside. So here we are on the far side of the Buzzell Mill. This is where the water would exit from the Buzzell Mill. This is the tail race of the Buzzell Mill. And the water, this used to all be a canal. You can see the edges of the canal here. And we'll show you in a minute where that water went in to the Belknap Mill. The water came from under the Buzzell Mill. This was all open then, and you can see these two arches. They actually had two head races where the water went in, and the turbines were inside. So we saw how the water came in through the mill, but let's step back a couple hundred years, maybe 100 years. Originally, the mill water provided power through something called a water wheel. And in this case, this is an overshot water wheel. You've no doubt seen bucolic images of water that would come down through here. This gate would go up, and the shaft would turn. We used water wheels for a couple of hundred years from when we first started. The very first use of water wheels were for sawmills, grist mills that made grain, grain into flour, and early businesses. So this produces something called rotary power. At the end of the day, that's always what we're after, is rotary power. A motor, an engine in a car produces rotary power. It's something that turns. It turns out though, whether it's an undershot water wheel where the water comes underneath the wheel, this is very inefficient because as the water level drops, it just slows down, goes slow, or if it speeds up, I mean, water wheels used to just get blown away in the spring sometimes. Overshot, you had a little more control because you had these gates that could control somewhat the flow of the water, assuming you had enough. But it's still very inefficient because you've got these shafts, these long shafts, and these bearings, and then at the far end, it's just having rotary power extended that far. It was really hard on the equipment, and it's very inefficient. Efficiency is everything in motors because the closer that every amount of force turning that wheel can be applied towards rotary power, the most efficient you are. These were relatively inefficient. They were also subject to the elements in the winter. Try turning this with ice all frozen up, wouldn't work. So as time went on, our brilliant forefathers, and they weren't here, they were further south in Lowell, came up with a concept of something called a water turbine, which this mill had several of in the basement. And the water turbine, the water came in through the top. It turned out you only needed a 7.5-foot head, which is the height between where the water is coming in and where it can go out. So you don't need water falling off the Empire State Building to be effective. In fact, it becomes less effective the further it falls. Anyway, so this water turbine, which came online in Lowell and Lawrence back in the 50s, 1850s that is, middle of the 19th century, you know, really that's what we use probably for the next 50 or 60 years for in fact, they're still using variations of the water turbine out on the Hoover Dam and in other places because it's basically very efficient. Water comes in the top, it hits the vanes, and it keeps rotating. The best thing was, as you saw from the Belknap Mill, the water, once it leaves the river, it's all underwater. It's all covered. It's not prone to freezing up. So that solves one problem of running a water wheel when it's all iced up. The other is you can control the flow much more absolutely. Now, once you've solved this problem, that's only part of the problem in converting. And now what we're talking about is formally called hydropower. Power for anything made from water is hydro. Hydro is Greek word for water, hydropower. If you're making electricity, it's electric power. In our case, eventually it became hydroelectric power. But for now, through close to the beginning of the 20th century, it was just hydropower. So what do you do with this shaft that's just sticking up, turning like mad? How do you get it to right angles? Because that's how your mills have to operate. They have to, anything, you really want horizontal power. So how do you go from vertical to horizontal? And that's what these lovely babies are. So down in there is the base of the shaft for those turbines. And they come up through to these angle gears. These are beveled gears, and they're just like the rear end of your car or your truck back in the day. This would be the motor in the middle, and these would be the two wheels. Only now it's taking rotary power, vertical rotating power, and translating it to rotating horizontal power. Brilliant. So we've solved that problem. Not only that, but we've coupled together 3 or 4 of these. So that now you've got 3 or 4 of these turbines. So if one even for whatever reason clogs up or something like that, you still got the rest. They simply throw a clutch in here, just like the clutch in a standard car. They can release one set of wheels. It isn't perfect, certainly. They might have to shut down the line, but they try not to. One of the problems is if something causes that wheel to seize up, you don't want these gears to break. This is very expensive if this gear is to break. So just like in a snowblower, they have they use a pin, a shear pin. In effect, they found that this ironwood from South America would break off before the metal. So if you just have to replace, if all these get stripped off, that's no big deal. It is maybe you're shut down for a day. But if this breaks, first place, these are cast 150 miles away in Western Massachusetts, where a friend of mine used to work. Number 2, you have to take all these pillow blocks and bearings apart and get something really heavy to lift these plate pieces out, press the gear off, or you're doing that while you've called them up. Well, they may have other orders too, so they'll have to put your order in line. Anyway, we're talking shut down for weeks and weeks, if not months. So this is a very smart little thing, having that. Okay, so we saw how the power came from the hydro turbines down below, came up through the floor and went at right angles, all connected to this shaft. Now what do we do with it? the point of all of this is we need to extract rotary power out of the water, out of the river. That's very cool. We've got water falling into the Winnipesaukee River Basin. We've got the Winnipesaukee filling up with water, and it's literally coming through the head race into the mill, and these things turn, and they're all connected. Now, originally, so much for the map. So, originally, this mill was all powered by pulleys and belts. And this is an example of one of the primary pulleys. This is all connected together. We'll talk about the governor and the shaft, etc. But what we can't show you here is that up through the building, there were these giant belts. These belts went around these, and they went up to every floor. There were counter shafts. There were 2 to 4 shafts on every floor that ran the length of the building, and they were all connected. And then, as we'll see in a few minutes, off those belts, they were all running the machinery, whether it's lathes, whether it's drill presses, or most importantly, for the Belknap Mill, knitting machines and other types of machinery. They all came off these shafts. They were all connected. It was ingenious, but take it from one who worked in a sawmill that was run through belts many, many years ago. I didn't work when it was running belts, but my father took me up into the Adirondacks to one of the Allen Rogers mills back in the 50s, and they still were belt driven, all the saws. And I gotta tell you, it was bedlam. It was noisy. All of these things whirring and slapping, and it was very inefficient. But that's what they had, and that really was what the country had in the 19th century, most of every manufacturing operation. And so it's no accident that Laconia is on a river. It's no accident that all the major cities in New Hampshire are on rivers, because they needed that power. And they had to be pretty close. You couldn't have manufacturing half a mile away. If you had shafts half a mile long, what would happen when people walked down the street? There'd be this big shaft out in the middle of the street. It wouldn't work. So all the mills were on the rivers. And we can see that. We can see the remnants in Lakeport where O's restaurant is. That was part of a big mill complex there at the Lakeport Dam. These Buzzell and Belknap mills, these are remnants. Down in Franklin, they have several mills that are still extant. And then you have other towns. The Manchester has terrific mills left on their rivers. Okay, so you saw how we got power, rotary power, and whether the big belts went up into the building. And here in this photo, you see those shafts that I was talking about that ran the entire length. This would be on one floor of the building. It might be the 3rd floor, it's who knows. But every one of them, in addition, had these pulleys and belts that went floor to ceiling to power the equipment. And there were others. You can see belts in the background running other things. Here's a whole maze of belts for a different operation. Over here we see a sewing operation, or knitting, excuse me. You can see all these belts along these pulleys, all running the various equipment. And now, mind you, when things are driven by belt, if something went wrong, you didn't have a safety switch that would just sort of shut things off. These big red buttons, and everything comes to a stop. No, there was a lot of latency, and I got to tell you, it was very dangerous. People lost fingers and arms, and it was very dangerous. This is a good example of the use of belts. This is part of the machine shop. This is a photo with Alphonse Mayhew, the nephew of J.P. Morin. But out overhead, we have a series of these belts. But for instance, you see a belt coming around, it's driving a lathe. And down here, there are additional, you move the belts back and forth, and you could change the speed of the lathe because you needed different speeds for the lathes. Now here's a drill press, and you can see this has a couple, probably one of them, you may have to have a carriage on the drill press, and you sometimes would change the speed. For big holes, you run it slower with more power. And so all through here, you have all this equipment. Here you could, generally you just have you could throw a clutch where you could just throw the belt in and out. But everything was done that way, but everything in the mill had to be fixed. So one of the most important people below the owner class were the millwrights, the people who repaired and built. Many of the machines were built either here or locally. Warren Hughes's father and grandfather ran Hughes Machinery right at the top of the old Mill Street Bridge there. It's now housing from Lakes Region developers. But they would often, that's what lathes are for. They might have to replace a pulley. They'd, shafts break. They'd have, just all these different things going on with these machineries. Everything that turned began in the river. Now, you have limitations ultimately because look at this complexity. Not only is it complex and dangerous, but all these belts, these are very inefficient forms of power. The conversion, and I'm not a physicist or an engineer, so I can't tell you what the coefficient of the efficiency is. Maybe your teachers can assign that to you. With the power flowing by that river, how efficient, how much are they getting out of it? So eventually, they figured out a whole new way to deal with that. I was mimicking what a skater might do when she goes into a twirl, or he. And you'll see this anytime you watch the skaters. Their arms go out and they slow down. When they want to speed up, you'll see they bring their arms in. That's called conservation of momentum, which is another physics principle. Physics is a wonderful subject. I loved it. I still love it today. This is just the opposite. What happens if the river starts running too fast? You don't want these poor knitters to deal with machines that are just going crazy and spinning out of control. That might be fun for a few seconds, but a lot of things would start breaking, including people. So somebody figured out quite a while ago how to turn that conservation of momentum principle into a speed governor. Now they use speed governors in a lot of other types of applications, but it's especially important. You would set this so that if it started going too fast, the balls would start to rise up, and as it rose up, it would release a clutch. The clutch would cause this to slow down, which would actually literally slow down the whole process. And it really didn't take much, because for the most part, rivers don't start and stop. If you know there's a flood coming, you'd just shut down the mill and pray that it didn't take the building with you, which did happen. I mean, that was the downside of building on a river. So this is a speed governor, and that's how things work. Now, eventually, remember I said you can't have a shaft half a mile long. People figured out the principles of electrodynamics. Principles of electrodynamics are that you can create electricity by turning a magnet in a bunch of wires. That's called a motor. And we do have demonstration projects that we'll get to soon. You reverse that and put electricity into a motor and the shaft turns. So you can go either way. How do you know that? If you look at your car, how do you suppose your battery gets charged? You have an alternator, which is a generator. So you have the belt coming off your car, or a gear in some cases, fan belt, turns this little tubular thing, which is a generator, and it creates electricity which goes into the battery. Similarly, if you took a battery and hooked it up to a motor, the motor would start turning. And they actually, once they figured those principles out, back Edison and Tesla and others, boy, this thing, the changes came in a hurry. They couldn't convert mills overnight, but here at the Belknap Mill, beginning in the late 1890s and for the next 20 years, they tried various conversions. Basically, the most important parts were to create electricity. For instance, lights. Until we had lights in a mill, you couldn't operate at night. You couldn't have candles in a mill because mill produced an explosive dust, just like flour mills. So that's why you see the tall windows on mills, schoolhouses, the old schoolhouses. Most houses had small windows to conserve heat, but in schools and mills, they had tall windows to maximize the amount of light. People worked longer hours in the summer because you had more light. You know, you could work till 8, 9 o'clock at night. Long day for some of these folks. So how do you get electricity out of the river? Well, we've got almost everything we need. We've got the rotary power. But instead of these belts that go up there, we have these electric generators. Now this electric generator has, you can see these two wires coming out of it. This is a pulley that came off one of these big shafts. So this would turn, and what you see in here, these are all the coil windings in there, and in the middle are these electromagnets. And as those rotated, they generated a tremendous amount of electricity that came out through these wires. And that provided hydroelectric power. So we go from the river, which gave us rotary power, used to be just from the belts that ran the mills, but then once they figured out how to create electricity and tame it, they created electric generators. And then they turned this principle around slowly at each station upstairs. They then could run wires instead of big belts up through the floors. And those wires would come down to the individual machines, and they would have electric motors, which is just like a generator in reverse. The electricity goes in, the motor starts to turn. It's a little more complicated than that, but the principle is identical. Still is.